Hey everyone, I'm Ryan, and I want to talk to y'all today about how we've been able to leverage HyperX along with its capabilities for manufacturability to kind of design some of the most performant bike components on the market. Kind of a practical application of some of the features that August showed yesterday. So if you were here at the last users conference, you might remember seeing me up here. I was talking to you about kind of how we had scaled up HyperX's capabilities as an employee at Trek, where I was a member of the performance research team, kind of across a bunch of different applications. But now I'm coming to you as an employee of Collier. So I have been working in the Raleigh office as a structural engineer, but I'm also lucky enough to kind of share work with some of our German colleagues on general composites applications. So members of the team that I've worked alongside, Johannes is a research engineer in our German office, and he did a lot of the producibility work that I'll be walking through today alongside me. And then Bertram is our director of advanced composites at the German office and was kind of doing some of the advising work. So just to kind of lay the groundwork on why we're integrating with manufacturability and maybe some of the differences between aerospace applications. So to set the stage, there's a little bit of a difference you might see here between aerospace, where you're dealing with large, comparatively simply curved panels that are all kind of tightly controlled with their layup process, their angles and things like that, versus what you can see on the right in those videos. You've got a lot of kind of hand layup going on. You're using kind of very tight curvatures and very localized stiffeners and strength reinforcements. So kind of understanding how plies are laid up and how they're positioned over that curvature can affect the performance of that ply pretty significantly, and that's kind of the impetus of incorporating DFM into our analysis workflow. So kind of what I said I'm going to be focusing on today is how we've been able to leverage HyperX's capabilities and its integration with CAM tools to balance stiffness, strength, and now manufacturability into our optimization workflow to make the best product possible. So what we are going to be looking into today is kind of the prove out of this workflow is an integrated bar stem. So this is for a road bike, and this has become more kind of ubiquitous in cycling OEMs as they look, I guess, one, to reduce part count on bikes, but also as they're looking to eke out every last gram of aerodynamic drag and weight in a system. So traditionally, they start up on the top right. You can see they're usually two pieces, but that increases overall system complexity, weight, and it's not as aerodynamic. So they're moving towards what you can see on the bottom, which is a one-piece, what we call a bar stem, which I guess is not without its challenges because it increases overall part complexity from a single standpoint, but it's more efficient from a weight and stiffness perspective. And I guess kind of a key thing to note here is this is one of the primary contact points for a rider. So from both a load and a stiffness perspective, it can pretty significantly impact their perception of ride handling. So you want it to be stiff enough so when they're sprinting at the end of a stage like you see here, or going around a corner at 40 miles an hour, you want it to be just stiff enough that they're not kind of feeling the bike squirm underneath them, but not overly stiff such that their arms and their bodies get fatigued over a full day of racing. So just to give a kind of high-level overview of some of the non-traditional aerospace applications that we've stretched HyperX's legs in with weight critical or stiffness or highly curved surfaces. You can see on the left, Yvonne showed this yesterday, it's the SP80 sailboat, so kind of a weight critical application with a lot of curved panels that we use to size the hull on. And then on the right is the Trek Madone, which you might originally think, okay, it's just a kind of one stack laminate structure with tubes, but the more you look at it, kind of the more complex it gets. So that's kind of what I'm trying to illustrate there. You can see on the left, there's some instances where we have as many as 7 different tubes kind of joining in an intersection at one point. Those all have unique fiber reference orientation directions. You might have global plies that span different sections that have different material reference orientations, like you can see in the right. You've got a single ply that spans 2 of those tubes. So you've got to deal with how you resolve those discontinuous material reference orientations, how you deal with drapability and things like that. So just kind of to show how complex the problem can get and kind of what we're going to be working on. So even though what I'm showing today is just a road bike handlebar, the applicability is that it can be scaled up much more beyond that. So I guess just to kind of level set where we're at in terms of how sensitive we are to weight. I know a lot of the presentations that we've talked about over the course of the last 2 days, we've been talking about hundreds or even thousands of pounds. And so I did a quick calculation. And so like the nose cone, just printing out the 150 pages of stress reports, that's probably about the weight of a bike frame. So we're about 500 to 1,000 grams. So in this case, like we're looking at taking out like increments of paper clips is a big deal of weight to kind of take out of this structure. So there's a lot of applications for very weight sensitive, complex curvature, especially in the sporting goods industry, whether we're looking at like hockey sticks, bows, or even stiffness constraints in auto sports like F1 or SailGP. So I'm going to dive into the case study that we're going to look at with the handlebar. This is kind of how it's set up. You can see on the top left, we have it broken up into kind of initial subpart structures. That's based on how we would likely see it laid up and manufactured. So usually vendors will break this out into green subparts with preforms, and then there's male and female ends that are joined together before it's bladder molded. As far as load cases, we've got both stiffness and strength cases to kind of simulate, I guess, both ISO standard strength cases, and then a lot of the stiffness, like I was talking about, it's very critical for rider perception in the end. So kind of talk about the workflow. There is a lot going on here, but we're only going to look at one of these. I guess the key point I wanted to make here, in this kind of diagram, the blue is feed forward, the gray is feed back, and each one of these workflows in a general composites application sense has its own use case for designing performant laminates. And so what we're going to be looking at today is kind of this orange workflow. And what I want to emphasize is we're going to start kind of at a global level. So from a whole bar stem perspective, we're going to look at composite element optimization to get piecewise stiffness and strength contributions of each of those different structures that I just mentioned. And then we're going to break it out into subpart designs. So once we do that, traditionally we would use a global ply builder approach. That's a ply-based approach. If you were here last time, you might remember me emphasizing the whole part is kind of the design space, so we can drop plies however and wherever we want within reason. So that's why we're going with an initial ply-based approach. But what I want to get into and what we're going to discuss today deviates from that traditional approach is the use of off-axis plies to aid in the manufacturability attempt. And so that's going to differ a little bit from what we're typically doing. To kind of develop a new optimization workflow for those manufacturability considerations. So to give an initial overview of those global optimization results, you can see here this is just ply distribution if we consider just stiffness, if we just consider strength, and then the combined load case. And the number on the bottom is kind of a relative performance metric. So normalized and higher is better. So this is just showing if you consider just stiffness or just strength independently, it's not as optimal of a solution if you end up trying to go back and add plies to recover stiffness or add plies to hit strength targets. So kind of emphasizing that it's both a strength and stiffness driven problem. And so we used Hyper-FEA pretty extensively in the end. Today, I'm going to focus on just the drop subpart. That's one of the structures. It's doubly curved, very stiffness critical, and so kind of a good example of this workflow. So to talk about how we're balancing manufacturability with analysis, we're kind of using an iterative workflow with CATIA in this case. You can also do it with FiberSim like August showed yesterday. And we're leveraging those integrations with CAM tools in order to take into account ply drapability and things like that with our analysis, kind of to take our analysis and have traceability all the way from kind of our computers down to the manufacturing floor while we're doing this analysis. So this is kind of a high-level roadmap of how this process works. So in this, the blue is actions that we're going to take within each software program, and then the green is outputs that feed forward into kind of the next step, which is why it's pointing to the arrows. So you start out with HyperX like you would with traditional part sizing. From that, you can generate your laminate families. You can generate virtual ply boundaries that you can then export into CATIA with those ply boundaries, ply sequencing information to do your producibility studies. You can take those producibility study results, whether it's a draping simulation, we can export CAD curves in CATIA and bring those into HyperX. And from there, that's how we really kind of take into account the manufacturability story. We can update fiber orientations with as manufactured intent with variable fiber direction from those CAD curves. We can use the draping simulation results for cut pieces and reassess margins before we kind of export those final design plies back into CATIA, where we can generate a ply book that can be consumed by our vendors. So that first step, HyperX can natively export ply boundaries. So you can kind of see on the left, that's a cleaned ply, an example of what you would get in Ply Manager and HyperX. And it's really as simple as just hitting the Fem to CAD button in Ply Manager. And what that does is that generates CAD curves that represent the boundary of the ply that can then be exported into your CAM tool. If you couple that with the ply table export in Ply Manager, you can take that into CATIA, you can take that into FiberSim, and generate your kind of stack up within your CAM tool. So once you do that, we can run producibility checks, variable fiber direction, and ply book generation. So this is kind of the initial result that we get out of HyperX and a traditional laminate optimization with a global ply builder approach. You can see the result on the left, ply managers in the far left, and those results as ply coverage are in the middle. It's suggesting primarily for stiffness that there's going to be a lot of global zeros or organic shapes to resolve those stiffness constraints. And so what we wanted to do here is generate representative large structure plies that we could then export those ply boundaries into CATIA to do producibility studies on. And so that's what you see on the right is those cleaned boundaries. The largest is about a 45 millimeter width, which is relatively representative of what we would see from vendors, where they're doing kind of like a clamshell approach to cover the whole ply or the whole structure. And we step down in 15 millimeter increments to get kind of some level of a sensitivity study for those results. So it's kind of the beginning of that balancing act with manufacturability. And so what we did with those representative ply boundaries, we did a draping simulation with those suggested 0-degree fibers. And what we saw is that with those kind of what HyperFEA or HyperX wanted, were not manufacturable with any width of that sensitivity study with the zeros. So we're outside of the shearing angle limits, and that was kind of the impetus of needing to go in and suggest off-axis angles. You'd have to otherwise do a bunch of different cut pieces and split this global ply into a lot of very fine, very discrete plies, which adds a lot of part complexity, a lot of weight for ply overlaps, especially when you're dealing with hand layup. So with that in mind, we kind of did the same thing except with an off-axis ply angle. So in this case, same boundaries, same shearing angle limits. All we did was change the ply angle to 30. And what we ended up seeing is that in contrast to the zeros, that no width was manufacturable, the intermediate and the smaller widths were showing as manufacturable. So that was kind of the initial promise to prompt us to go into further investigation for finding off-axis angles that we could use to replace those non-manufacturable zeros. and kind of balance that manufacturability aspect while still hitting our stiffness and strength as much as we could. So kind of another byproduct that we get out of that drapability analysis is while one of those 30s might show as manufacturable and drapable, what we have to keep in mind is over this complex curvature, there's actually a lot of fiber deviation going on. So if we start at the bottom and we work our way up with a full cut piece, you can see from the drapability analysis, there's as much as like go from a 30 to a negative 30, so 60 degrees of fiber deviation. So it's a balancing act of minimizing fiber distortion and also minimizing total number of cut pieces. So what we settled on was 3 different cut pieces over the length of that part to kind of meet our angle targets and also have a manufacturability part. So to kind of go into, now that we've identified a need for the off-axis plies, how do we go about actually sizing those? And so like I mentioned, traditionally we would go through and we'd use Global Ply Builder and Hyper-FEA to kind of do that, but those zeros weren't manufacturable, and Global Ply Builder traditionally only works with traditional laminates, 045s and 90s. So we have developed a new workflow that leverages laminate family capabilities as kind of an intermediate step to Ply Manager. So that uses laminate family trade studies, auto-generated laminate families that we can all leverage to identify off-axis ply angles. So this is kind of the workflow that we followed, starting at the top with a data interrogation from very coarse and working our way down to using automated tools and kind of more refined approaches. So we start off at the top with data interrogation. So we're looking at the initial sizing results. We're looking at thickness distributions, ply percentages, running loads, bending moments, kind of visually identifying where plies want to be and where those load paths are within the part. From there, once we've kind of looked at that, interrogated the model, we can break out into using some of HyperX's automated tools. So one is generating laminate families, traditional laminate families from those sizing results, which you can see in the top right. And we can also use the double-double laminate family generator that was discussed yesterday if we want to get kind of relative performance of those off-axis plies pretty quickly. And the end goal that we're trying to get to in the bottom is a modified off-axis laminate family. So we're identifying those off-axis angles that are most performant and replacing the non-manufacturable zeros in kind of the traditional laminate family with those key off-axis plies. So this is kind of how we started out. We, again, kind of used on the right, we had a coarse zoning. This is just to get relative performance of some of those laminate families. This was informed by drapability that we discussed earlier. And we're balancing kind of this need for stiffness to resolve those stiffness constraints with our manufacturability. So we kind of honed in on around 20 to 30 degree off-axis ply angle to meet manufacturability, but still have some level of confidence in meeting our stiffness constraints. And so what you can see on the right is the design study form. We used this, I think you saw yesterday a little bit. And this is just a quick way to perform rapid sizing iterations and get relative performance in both kind of producibility and mass of these different laminate families. And so we can see here, there's kind of an initial standout with this 25 degree off-axis laminate family that had the modified main stacking sequence. And so from there, we can kind of dive in and perform a more fine analysis. This is using composite element optimization. So what we do once we kind of narrow in on even tighter angles, candidate angles, we wanted to make sure that what we saw in the rapid zone-based sizing still holds true in a more detailed composite element optimization. And so what we can see in these results, that kind of confirms what we saw with the laminate family trade form, that the modified 25 degree off-axis is the most performant. And what we get out of this, again, we're not using Global Ply Builder, we're using composite element optimization. So that result you can see on the right is kind of a highly organic shape. And so while it's organic, it's still allowing us to optimize with these off-axis plies, even if it requires some kind of cleanup from the analyst at the end. So this is what that kind of looks like. HyperX is suggesting kind of localized stiffener ribs, and so it's kind of up to us to group those based on initial producibility. We wanted those 3 cut pieces and also group together those stiffening ribs in order to get kind of a manufacturable ply. It's also worth noting kind of the data interrogation approach. Even though we can't make full structure zeros, we can still use localized zeros as stiffener reinforcements to meet our stiffener goals more effectively. So we can look at the running loads for our 2 kind of most dominating stiffness cases and use that to kind of design where we place localized 0-degree preforms. So this is kind of, once we've got all of our plies together, we've got everything cleaned up, we're happy with how the stacking sequences, we're happy with how our margins are. This is where the manufacturability kind of really comes into play. So you can see we've got a representative ply on the left. We're happy with our margins. Maybe we have a few peaking elements, but we're able to take those exported ply boundaries, like I mentioned, that you can generate in HyperX, do your drapability analysis, and then what you see in that middle image is those CAD curves from the drapability analysis. We can bring that back into HyperX, and we can adjust actual as manufactured fiber orientation with variable fiber directions. And that's kind of what you see in that blow up picture. So the green are those variable fiber directions or variable fiber curves that we imported from drapability analysis. And then the initial kind of nominal angle for the ply is that black hash mark. And when we update that, we get the teal angle. And so you can see there's pretty significant deviation from as analyzed. We go from kind of an axial to a more transverse. And when we reanalyze our margins, we can see largely stiffness-driven negative margins. But it's important to note here that normally if we would have stopped on the left, we would have missed this entirely. We would have sent that off to the vendor. They would have tried to iterate that on their own and resolve that in a non-efficient manner, but now we can do that in-house. We can catch that early, we can catch that in analysis without even making a physical sample before we kind of send that off. So we can add plies to meet stiffness requirements. And once we've done that, we can port out the ply sequence, we can port out the ply boundaries, and we can generate a consumable ply book for our vendors. So what we end up with in the end, kind of overall, we end up with a product that's lighter, ahead of schedule, and kind of a lot of transparency and producibility. So relative to the initial subpart design, we were 10% lighter. We were 2.5% lighter than a traditional laminate design, all while reducing total ply count, so part complexity, by 6%. As far as schedule goes, we were able to do those coupled stiffness and strength iterations in HyperFEA ahead of time. So if we were going to do that at the vendor, it might take months. And to resolve those stiffness margins, it was about a week in HyperX. And again, very easy to do design trades and see those manufacturing considerations with variable fiber direction. And from a producibility standpoint, can very easily communicate ply books to our vendors for traceability. And we have the ability to make manufacturing recommendations for cut pieces, for drapability, and kind of transparency over the stacking sequence with laminate families. And that's it.
You showed in one of the earlier slides that you had a stiffness, a 0-degree stiffness ply that you were just able to add. Mm-hmm. Are you able, you do the drapability study in order to get the variable fiber directions, to get the real fiber directions.
Yep, yeah.
For when you add a ply like that or add a zone like that, do you have to redo it, or are you able to take the fiber directions from a previous ply or the ply underneath it and just apply it to that piece?
That, maybe Johannes could answer that question. He's in the back and he did some of the producibility analysis.
Well, actually, to reduce the effort to apply variable individual fiber orientations for each individual ply. You can just create reference plies, do the drapability on that, and then just use those curves in order to reduce it. Because I did for a previous project the handlebar, and you end up with like 400 individual plies. So when you apply all those cat curves on it, you don't even see the colors of the zones anymore when you zoom out. So so in order to do that, reference plies are actually the best way to do that.
Great, thank you.
When you were looking for the off-axis angles, I noticed you did the double-double. Did you find good angles there, or find use of?
Yeah, that was a step that we could use. I think in the end, kind of when we set up this initial course zoning, I think that it was maybe too restrictive in order to see some of those. So we were doing very fine with the double doubles, and so I think maybe it was too restrictive initially with this course zoning, and we would have benefited to be able to resolve some of those, I guess, stiffness problems if we would have refined the zoning a little bit better. So in the end, it was primarily looking at like running loads and bending stiffness to kind of identify initially, but I think more than not, it was the kind of producibility restrictions that informed the initial angle selection that we kind of show here and use the modified main stacking sequence. But yeah, to your question, I think if we had a more refined zone model, that would be where we would see benefits of the double-double.
Thank you.
Awesome.